So I call this Adventures in Optimization. And the way this will go is I'll talk a little bit about sort of the problem I was facing about me thinking about optimization. It's around the topic of hashes, ordered hashes or unordered hashes. And I'll kind of take you through my thought process that led me to develop a new ordered hash module that was faster than other ones, and sort of why it was faster and how I was able to prove and demonstrate that it was faster. So starting off the problem. Sort of as we know, Perl hashes are unordered maps. So you have a set of keys and values that are paired up, and the order that you get them is sort of indeterminate. In fact, they are random and becoming more so. So if we think about this little script up here, this one-liner, create a hash with the values 1 to 10, so 1 pairs with 2, 3 pairs with 4, and so on, and then just dump it out. And on Perl 5.16, you'll notice that the order you get things out doesn't have anything to do with the order that they went in. Think about then across multiple runs. So this is 1 run, 2 runs, 3 runs. On Perl 5.16, a small hash like this always gives you the same order: 13795, 13795, 13795. Many of you may be aware that in Perl 5.18, hash order became randomized. 59731, 73519, 91375. Every invocation of Perl is going to give you a different order of the hash keys and values out for that process. So every new process invocation. And if you modify the hash, I believe you also, that may also expected keys to come out in a certain order, and broke under 5.18 when the keys came out in a different order. So okay, that's fine. You know, as long as you sort of know that you can't depend on an order. Perl hashes are very useful. We use them all the time. But what if order matters? And this sort of actually becomes very important for me, because at MongoDB, commands sent to the database go as an ordered map, key value pairs, and the command that you're executing on the database has to come first. So if this is insert and a collection name and a bunch of other values, and it suddenly shuffles around, and one of these parameters winds up first when it hits the database, it's going to be an error because it doesn't recognize that command. So it needs to have an ordered map. But there are other instances beyond MongoDB. I maintain HTTP Tiny, which is sort of a tiny HTTP client. And one of the requests I got as a bug fix a year or two ago was to make sure that if somebody gave an array reference of key value pairs for parameters, to make sure that whatever one was first actually showed up first. Because apparently there are some APIs in which this matters. And even though the spec says that the order shouldn't matter, there are some services out there that if they get the wrong parameter first, blows up, don't know what you're talking about. So sometimes order does matter. But it's not free. So what can you do to get order? So one of the things I talked about in HTTP Tiny is to use an array. You have an array of pairs. That's great, but you don't get random access. Another thing you do is you can use an object and sort of have the object encapsulate the mapping as well as the order. You can also use tied hashes. And so it looks like a hash, but actually it preserves order. And the downside of that is that you have tie overhead plus the method call overhead that you get with objects. And you'll see a lot of that in the benchmark. So tie IX hash, which I'll call Xhash for short, is a pretty popular, well-known tying module for giving you an ordered hash. And so that was kind of the place that I started. The MongoDB Perl driver that I work on actually supports it natively, so if you pass it an Xhash object, it will treat that appropriately and serialize it as an ordered data structure. This is kind of how it works. So the tie interface, you'd say tie my hash to the class. You could give it some starting data. You can sort of add data that gets appended on the end. You could say the piece coming out of it first, and it all stays ordered. The object-oriented interface sort of skips the tie, but uses the same object underneath. So you simply create a new Xhash object, passing your data, and now you can push new data on, or you can use the fetch method, which is what underlies the hash, tied hash fetch, to pull the data back out. So that's tie Xhash. But I found some problems with it. So first, if you use it in the tied way, it's very, very slow because of the tie and method call overhead. I also thought the object-oriented methods were kind of ugly. All of the basic hash functions are capital letter methods because that's what implements the tie interface. There was no good way to copy. If you wanted to make a copy of an Xhash object, you had to basically read out the keys and values one by one and stick them into another object. which is pretty heavy. And there was no iterator. There was actually no easy way to just sort of say, hey, I want to iterate over all these the way you can with like each on the hash. So I thought, all right, well, doesn't seem that hard. Maybe I could patch it, put it in some sort of a copy. So I went and I looked at the guts. So this is just the new, or the tie hash method, which sort of creates the object. And I immediately had kind of a WTF moment. We have a hash reference that's the index. They have an array of keys and an array of data and an iteration count as it goes through. So that kind of looks like this. If you sort of take a new Xhash object with A1, B2, C3, D4, you have a hash that sort of maps A to 1, B to 1, C to D3, and two arrays, one with the keys and one with the values. And that makes things really expensive. So a fetch, a simple fetch, this is the fetch function, exists, blah, 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 blah. You have an exist call, a ternary operator, and 60 references just to get one value out on top of the method call overhead. That's a very expensive fetch. And again, you'll see that later in some of the benchmarking. And also, you have a very expensive store. So now you have to sort of check to see if something is this. So now you're doing dereferences all over the place, and you have to store the key and the value. You're storing and the key can actually has to get pushed in here, and added into a hash with an index. Very expensive store. And if you look at this a second, there's something kind of odd. And it's here, which you can't really see because it's highlighted in red but doesn't show up. My I is this value, so get the index value of this thing. And then we go and put I right back in the same place. So I is this, and then this is I. No change to I in between. They just sort of pull it out and store it back. Don't know why. Funny stuff like that. And that was like just one place I happened to spot check. So what are some alternatives? Another module on CPAN is tie-LL hash. Tie-LL hash does this. So same sort of tie the hash to class, A, B, C, D. It creates a hash with the keys. The value is a reference to a hash reference. The hash reference stores the value and a previous key and a next key. It's a hash of doubly linked list. Which means that you have to do a memory allocation every time you assign something into it. So every time you create a new node, this is the last function, which puts something onto the end of the list, or a push. Create the new node. And your self node's new key is a hash reference with all these values. So you're having to do a memory allocation every time you store something new. And also you see a lot of dereferencing going on with the rest. So then there's array as hash. Which I thought, oh, this looks kind of good. It's kind of interesting. And its data structure is actually pretty simple. So it keeps an array of key value pairs, array reference, key value pairs inside the object, and it has an index to it. So A goes to 0, B goes to 2, C goes to 4, D goes to 6. So you have a way of kind of getting into each of those sort of elements. And if you want to get the value of A, you look at sort of A plus 1 to pull that out. Seems pretty reasonable, but as I started digging into the code, it's actually pretty bad. So up here, key, this is the get method. Key equals self, and then the dereferencing the code reference actual key of the key. So for every key, you have to make another subroutine call down to here. And that subroutine call, if your key happens to be a reference, it will conveniently call refadder for you from scale-util. So if you have a non-reference key, you automatically get one extra function call. And if you happen to use references as your keys, which is sort of a nice feature, now you get 2 function calls. So another very heavyweight access to values. The other interesting thing is that if you only want one key, this get method is designed to give you one or more keys. So if you only want one key, we set up an array, and then we push a value onto it, and then we pull the value back off and hand it back through the return. So a lot of memory allocation, we got to push, now we're calling want array, where all this sort of stuff has to go through just to hand back one value. So then there's tie hash indexed. I thought, all right, keep moving through, maybe I'll get something good. This is XS. I was excited. Okay, an XS module, which is good for certain circumstances, not good if you need pure Perl. But I thought, okay, this is great, but it's flawed. So it essentially is the same data structure as tie-LL hash, a hash to a linked list, except the linked list is all C structs. So it takes the hash, and where it would normally have a pointer to this Perl value, instead it's a pointer to a C struct, which comprises a doubly linked list. So it's completely opaque. You can't dump it. Its tests happen to fail since the hash randomization, so you can't even install it from CPAN without forcing it. And as it turns out, when I started doing the actual benchmarking, we'll see later, it's actually not even all that fast. Not really sure why. So what else can we do? Then I started getting pretty deep into what the other alternatives are. All of these are somehow sort of special purpose thing or weird. So this uses array elements, but it splits them with a certain separator. Tie-hash array, you can only get them alphabetically. So it's an order, but it's one particular order. It only comes in black. Tie insert order hash and stored order hash are essentially sort of just inverses of each other. This one, you get it ordered by insertion time. And this one, you get it ordered by the last update time. So if you're doing some sort of LRU cache, maybe this might work for you. But like, it's a very special purpose thing. Array assign, sort of similar to array as hash, but the set of keys is restricted to other sort of weird stuff. Array OR hash is one of my favorites for crazy. Internally, it keeps a tied array and a tied hash. And it uses array and hash reference overloading so that if you call hash brace value, that dereferences the hash and returns the tied value underneath so that that tied value can then dispatch off to its fetch methods. And I didn't even bother to benchmark that one. No, actually I did. You'll see. So I think I did do that one, actually. You'll see it does not perform well. Data pairs keeps an array where every element in the array is a hash reference of a key and a value, which does purport to solve the problem of duplicate keys being allowed. Data OMAP, I think it was another one of those, but doesn't allow. This one allows duplicate keys, and this one doesn't allow duplicate keys. And then data XHash is a blessed tied hash worth with doubly linked list. Again, so done in a slightly different way. So a lot of sort of weird stuff out there. And my general feeling is that complexity is bad. Some of you know that I'm a big fan of tiny modules. I like to sort of write the smallest modules that can deliver the most bang for the certain lines of code. So I was thinking, what's the simplest thing that can work? And for me, it's this. Bless the hash reference and keep an array of the order of the keys. It's pretty straightforward.
Pseudo hash.
Yeah, very much like a pseudo hash. Straightforward. But I couldn't find it on CPAN. After digging through all this stuff and chasing it, and it might well be there, but I couldn't find it. And so as Damien says, I wrote it. And this is called hash ordered. So this is to follow that same sort of diagram I did before. The data is all here. And there's an array that says what order do we want these things in if we have to iterate over it in order. Pretty straightforward. It means it has a very cheap get. So this is just 2D references. Go to the data hash, pull out the key. I don't have to check for exists because that happens automatically. If it's undefined, that'll just come back. If it doesn't exist, that'll just come back. No problem. Very, very cheap. And store is pretty cheap. In store, I have to check exists because if the key doesn't already exist, now I need to sort of push it onto the end of the list of keys. But otherwise, it's just, yeah, we'll go set it to that value and return it. So this is comparable in its complexity to the fetch in Xhash. And usually we think store is a lot more expensive than fetch. So already, sort of, if my store can be as efficient as the fetch in Xhash, I think I probably have some efficiencies there. My shallow copy was straightforward. This is the clone function. The first clause here is sort of if you want a subset of keys, it'll do that for you. But if you just want everything, it just create the same data structure again and bless it, and off you go to the races. And an iterator was straightforward as well. Get my list of keys, get my data reference, return a code reference that's an iterator that returns undef when it's empty. Pretty straightforward, and it returns key value pairs. Very, very straightforward. Not a lot of lines of code. Here's the rub. Delete is very expensive. Because the array of keys doesn't have any sort of index, if I need to delete a key out of the array, I have to search the array, and that's and that gets expensive as the array gets larger, because it's just going to iterate through the array until it finds the key and then delete it out. So I think it's a pretty good trade-off. It's about 130 lines of code. So it is sort of like tiny in the sense of some of the tiny modules, though I didn't want to call it that because I think somebody actually has a hash tiny that does something else unrelated. It has a faster get and set than Xhash, faster copy, slower delete, but my experience is that I don't tend to delete things out of a hash a lot. That isn't sort of like maybe a little bit like you construct a list of arguments, maybe you delete an argument out, but you're not creating an array of thousands of things and then deleting lots of them out. But I'll show that in the benchmarking later on. So the next question I had, having written this, which I thought was faster, but I don't want to just sort of believe that it's faster. I want to actually show that it's faster. So the first point to make is people probably already know this. Benchmarking is not profiling. So when we are profiling, we're looking for hotspots in the code. So we're saying, well, of this code, where are the hotspots? Where is the time being spent? How can I fix those and optimize those? When we're benchmarking, we're comparing how do these two different pieces of code compare. And scale is really important in benchmarking. And so in the benchmarks I'll show you, I actually sort of tested a number of different scales, because if you have sort of a big O problem, and I'm going to use that loosely, I'm not going to get into whether it's O or theta or omega or the variations. If scale is something that matters in your algorithm, like in the delete, you want to be able to see that. If you just benchmark everything at, at a 10-element hash, maybe it all looks the same. Do the same benchmark at 1,000 elements, you start to see a very different performance. So I wanted to test at a number of different scale points. And then constants matter. Even for things that should be constant, like hash lookup, the constants matter. The 60 references versus 2D references starts to really make a difference when you're doing things like that. So these are all the different combinations I wanted to benchmark. I wanted to look at the different ordered hash modules. I picked a subset that I thought were plausible for general purpose. I wanted to test all the different sort of basic operations. I didn't test sort of the push and the unshift and other things that were combinations of the primitives. I tried to stick with the primitives. And I wanted to test at a number of different scale points. And rather arbitrarily, I picked 10, 100, and 1,000. I think a lot of Perl hashes are in sort of that general size range, unless you're using a Perl hash for a very, very large data structure. And then, if you want that to be ordered, you're probably paying, a high expense cost you probably shouldn't. So what are the benchmarking tools? Who's heard of benchmark.pm? Who's used benchmark.pm? The same number of hands. So benchmark.pm is a benchmarking module that ships with the Perl core. It's been around for a very long time. DumbBench was written by Stefan Mueller to try to deal with some of the situations where benchmark.pm doesn't work very well. And there's some other stuff on CPAN. But all of these other tools, and even benchmark.pm itself, have what I think is a fundamental flaw in benchmarking, is that we shouldn't make assumptions about the distribution. Right? So the timing distribution you get in a benchmark may not be normally distributed. It may not be nicely distributed. I've experienced problems with DumbBench on things that appear to be bimodally distributed. So I have sort of two peaks in the timing output. It's either running over here or it's running over here. And DumbBench is trying very hard to find a median and get it to converge. It's just bouncing around, never converging. So the right way to deal with this kind of a situation when you have distributions like this is to use something called a Kolmogorov-Smirnov test, or KS test, which is a comparison of the empirical cumulative distribution functions of the timing data. It's non-parametric, so it doesn't assume any particular distribution shape. It works to compare distributions of unequal variance. Why would this set of code and this set of code give equal variance in the results? There's no reason to presume that. And it's very sensitive to both the location and the shape. So if you have a distribution of timing that's nice and smooth, but another one that's a big peak, KS will tell you that those two are different, even if their mean or their median is exactly the same. But it doesn't exist on CPAN. Right? No. I haven't written it yet. I really, really want to. I've like half written it, but KS is actually be very slow unless I write it in Access. So at some point, I'm going to write a KS benchmarking tool for CPAN. And it won't require you to run things thousands or hundreds of thousands of times. You can run it like 100 times here and 100 times there, and get the statistic and have a nice statistical benchmarking result. That will be a feature. So I decided to keep it simple and stupid and go with benchmark.pm. All I really wanted to see was just time. So the problem I have is that benchmark.pm, the way most people use it, is very verbose. You can kind of say, compare this and this and this and this, and it gives you this nice matrix. Like here's A, and here's B, and here's how many wall clock seconds and user seconds and system seconds and CPU, and here's the number of iterations, and here's how many time I ran each one, and here's this little matrix, and here's the percent differences between the two. And like, that's great, but if you think about all the variations I wanted to do, different modules, different scales, different operations, the matrix would just be completely unreadable. And there's a lot of detail I just don't care about. Like, this is, I suppose it's interesting, and maybe it says something to some of you, but for me, I just was kind of interested in, like, just on a raw basis, how fast can this thing run? So my approach was to break it down. Given a hash of test labels and code references, output the timings in descending order, and repeat at different scales. And I'll walk you through some of the code I used for that. So this is kind of the timing harness itself. So using benchmark and the countit function, there was a constant for how many CPU segments I wanted to run. And then essentially this is the guts of it. Your result is the countit function on some subroutine you pass into it. You get a number of iterations out per second by computing it this way. There's a 1 to the minus e minus 9 fudge factor in case for some reason the resolution of the timing says it was instantaneous, so we don't want to divide by 0. So that's it, and then print out the results. And then I wanted to use varied but constant data across all the runs. The problem with tests like A1, B2, C3 is it's not very interesting, it's not very challenging. It's all like just single byte stuff. So I wanted to throw things that were very different. I decided to do it with random numbers. So I used the math random MT auto, which is a very good Mersenne twistor random number generator. And I just said, OK, for 10 elements, 100 elements, 1,000 elements, give me a structure which essentially is, for a 10-element hash, give me a structure which has random number pairs 10 times, and then 100 times, and then 1,000 times. As I think back on it now, maybe this isn't sort of the best varied thing. It's probably has lots of very big numbers. There's not maybe a lot of variation there, but at least I wanted to have them be different and not have it be all the same key or not have them be all small or have it be all big. So I wanted to vary it up. If I did it next time, I might do it differently. But that's how I did it for this time. So this is an example of benchmarking hash creation. So I looped over the different sizes I wanted to test, the different scales. And then I set up the hash of values I wanted to run, and then ran it. So for instance, this is just a subset. So this is HO is hash ordered. And somebody just call the constructor, pass in the data. And so the data is all out there, and it gets passed in, and the exact same data is used for every single one. Sometimes when I see people do benchmarking, they're actually sort of generating the data in each one, and then it means you're actually benchmarking things with different input data. Trying here to benchmark with exactly the same input data on every one. And then I went through the rest. So this includes some variations. So you'll notice I have like underscore OO underscore TX. TIX is TIX hash. Underscore OO means I'm using the object-oriented interface. Underscore TH means I'm using the hash interface. So I was testing certain models that had variations, testing it both ways to see what impact that had. What's nice is you'll see later on, you can actually sort of see the impact that using the tied interface has over using the underlying method calls. For fetching elements, it's kind of similar. First, I pre-generated all the hashes, so because I didn't want to include the hash generation in the benchmarking. And then I generated a set of test keys that I would look for. So this is getting about 10% of the number of elements and doing fetches on them. So randomly give me 100, give me 10% of the elements, and then go out and fetch them. And then the actual fetch code is just the fetch across those keys. So get the key, fetch the key, pull it out of the hash using tie. Whatever the right, most idiomatic method is for that class was what I used to then do the benchmarks. It was as tight as I could do it. That worked for fetch. It doesn't always work, but I'll come back to that.
The fetch, when you did the fetch, it was all existing keys, right?
All existing keys. I wasn't testing for non-existing keys, which would be an interesting test as well. But in this case, this was what I tested. So deleting elements is where I had to deviate from that. And this is actually a limitation of benchmark down here. So the problem is we can't isolate the delete, right? I need to create a hash of stuff, and then I need to delete a bunch of stuff out of it. And if I want the test to start with the same input data, the same starting hash, I have to generate that every single time, because this subroutine is going to be called thousands of times over and over again. What we really would need for benchmark.pm or a better benchmarking module is the ability to set up some test data outside of the benchmark timing, pass it into the benchmark timing, and just run the benchmark timing without. But benchmark.pm doesn't do that. So the delete tests, I had to actually sort of merge creation timing and delete timing. So in the results, you'll see modules that performed really well on creation tended to float to the top of the deletion benchmark as well. I still think it was pretty good for showing some differences. So we'll talk a little bit about the results. Before I go there, I'm going to get a sip of something. And does anybody have questions about anything I've said so far, or the stuff that I've talked about, or how I'm doing this? Or critiques. I'm welcome to have your critiques as well.
Add these function and exactly so you're simplifying out the descending order and those things.
I found that with the when I was playing around with it, it was getting that situation where there was just too much data, and though benchmark.pm lets you turn on or off certain formats, it was either way too much or like nothing. Like I couldn't just get like the iteration counts, and I was planning to sort of like pull this out and stick it into a documentation in a pod file. So I wanted to like have it be pretty spare, and I just was fighting with benchmark.pm. I would have to like monkey patch, and I was like, you know what? I'll use its underlying functions for timing it, and I'll produce my own report. This is Perl. It's a practical extraction reporting language.
In the hash tiny, I know it's not called tiny, the thing that you
Hash order, yeah.
I forgot its name already. In the getter, and in some of the code, I saw X's list copying and creating lexicals when they're not really needed instead of just using shift and then object deref on the shift.
Or even just the first element of the @ underscore rep. Yeah, I did not do have not done any of that optimization. So when I was writing this, I was really focusing on having it be as readable as possible, so that it was like very, very clear what was going on. And sort of then I did the benchmarking, and I haven't gone back to actually sort of do that.
And in some cases, it looks like you're copying lists instead of you taking array refs and moving array refs. It looks like you're using list context in some places.
In some places, it might be.
I think in the delete you were using list context a lot, and you may have copied over 2 or 3 times an array of the keys or something.
I'll look at it. I'll check. Like I said, I was not super careful about all that sort of stuff because I was aiming for more of the algorithmic variations. But there is a second wave of optimization that can do. That's actually where profiling could come in handy. Is actually sort of figure out what's really hot.
And now, of course, you'd have to have a lot of elements for a list copy to become punitive. So.
Yeah, I mean and you'll see that in the delete benchmarking where it actually performs pretty well for small size hashes, and only when you get to like 1,000 elements does it go and plummet off. Yeah.
Can you do the presentation on the profiling part?
Possibly at some point. Tim Bunce had a presentation from YAPC that I think is on Real TV, whatever it is, that was actually good. So talk about profiling. That would be a whole other presentation. How many people would be interested in a presentation on profiling, whether it's by me or somebody else? How many people would be interested in giving a presentation on profiling? All right. Eric, that's you. Eric works with me at MongoDB, and he's actually been doing a lot of benchmarking and profiling there, so he's been learning in more time. So all right. Other questions? Or should I get
I just had a quick question about the right toward the end there too about how you trouble isolating the deletes.
Yes.
We were not able to just pass in the same. You generated that random your data set. We're not able to pass in the same data set repeatedly. Or I mean, did I misunderstand why you do that? I say, okay,
think about it now. That code ref could have done a call out to somewhere else that gets it passed in, but I think even that would come in might be able to do that in a way that's constant, but then I'd have subroutine call. It needs to be better. That's
okay.
Clear.
I was good.
That's I'm gonna remind me at the end about fixing delete because you just gave me an idea for a way I think I should do that in a way that'll give it a better benchmark. Cool. Yes.
Did you look at Plaque's hash handler? I think Plaque request has like hash multi-value or something.
I did not.
Okay.
I did a bunch of meta CPAN and searchcpan.org searching on hash and ordered and various other sort of cognates, and I was chasing the C alsos of all those, and I didn't see it. So.
Yeah, I know it tackles the like multi-value thing and like it probably touches on our ordered stuff because Catalyst is the same thing where it needs the parameters in order and supports, I think URI PM also supports like A equals 1 and A equals 3 and A equals 5 and turning that into an array.
I think that may have been the thing that I've seen. I saw a couple that were, if you sort of store the same key multiple times, it turns it into an array reference, which I would count that as another special purpose one because you don't want that in a number of cases. Any other questions? All right. So now we'll talk about some of the results. So this was my first experience, Wipeout. And the lesson learned from this funny picture is, don't web surf while you're benchmarking. Leave your computer alone. Don't put your Perl processes in the background while you're trying to benchmark stuff. You get crazy results. Like one run it would work, one run it wouldn't work. The hash order would do great on size 1,000 and terrible on size 10. I then learned, set the benchmarks running, walk away. So let that be a lesson to you all. Don't web surf while benchmarking. Particularly don't watch things on YouTube. So this is just the abbreviations. You saw some of this already in the earlier code, but hash ordered is HO. It's actually just the kind of the initials with only a single colon. As a reminder, hash ordered is the data hash plus keys array. Array as hash is the flip side of data array and an index hash. X hash is the tie plus the hash, maybe the tie, not always, but tie plus hash plus 2 arrays. Tie LL hash is the tie plus the hash plus the doubly linked list. Tie hash index is XS, tie hash doubly linked list, but in C. Array ORD hash is the overloaded array ref and hash ref dereferencing, giving you back 2 internal private ties, depending on which way you're doing it. And data X hash is a tie plus a doubly linked list. So this is the creation benchmark. So in the creation of a hash of size 10, 100, and 1,000, pretty close to the top, tie hash indexed does very, very well. It's in the top 2 all the way across. So the XS module for basically blasting the data into the doubly linked list in C is pretty efficient, probably because it's avoiding the Perl op tree the whole time and because it's doing C memory allocation instead of Perl data structure memory allocation. Array as hash, which is the one that has the data key value array and the hash index, you can call that 2 ways. One way, you just pass it an array reference. So what does it do? It just sticks that array reference into the right spot of its object. So it's also very fast because it doesn't have to do anything. It just takes the array reference and passes it along. But it also has a copy method where you give it an array reference and it shallow copies it and it stores that. And that, not surprisingly, starts to be a lot slower. Hash ordered is here, sort of in red, all the way across. Other than these 2, XS or where the data is that you pass in is almost exactly the data that you're storing, it pretty much outperforms everything else, often by a significant margin. Certainly it outperforms tie X hash by 30, 40% on these sort of benchmarks, and pretty consistent across at all the different scales. What's interesting to me to note here, and you'll see this elsewhere, the difference between the fastest and the slowest, excuse me, it's about a 10x difference across this set of modules. 10x difference in performance just based on the underlying data structures and algorithms that it chose. So then we come to the fetch. Fetching 10% of the elements, roughly 10%. Hash ordered across the top blows everything else away. Even without the micro-optimizations that Bill pointed out, that can be done to make it even faster. It blows everything else away. It's comparable to sort of the data X hash in its OO implementation. Somehow the way it did its tie and linked list is actually pretty fast for a fetch. But certainly compared to X hash, it's a lot faster. And if you remember, array as hash was so this is the array of data and the hash index, but the one that called a function for every key all the way down the bottom. That extra function call to just to get the key to be able to look up the data absolutely kills its performance. So it's really fast to create them, but then very slow to get anything back out. And that's real. And to be clear, like I think that one was written by Curtis Poe, so he actually knows what he's doing. And there's a lot of design reasons why array as hash is doing what it's doing. So it's the underlying data structure. I actually don't think is that bad, but that particular implementation was pretty terrible. So then we come to setting 10% of the elements. So this is taking a hash and changing 10% of the existing elements. So these are all existing. This wasn't new. Again, hash ordered, with a very simple data structure, handily outperforms everything else. And interestingly, again, tie hash index. This is the XS module. Third, second, even though it's written in XS, somehow it's not able to do things as fast as hash orders. I don't know. I didn't expect that at all. I expected tie hash index to sit along the top of pretty much the whole time. And again, the array as hash bringing up the rear by a substantial margin. Like this is 520,000 to 164,000. Just off the bottom. Yeah.
Just a quick recap here. There's hash ordered is the one with.
Hash ordered is the one I wrote. So it has a hash reference of the data, and it has an array of the order of keys.
And which one was the opposite?
The opposite is array as hash, the one on the bottom. But it suffers largely, I think, not because it does the opposite data structure, but because it is doing a function call on every time it needs to get a key. It has to do a function call on that key first. I suspect just inlining that function call everywhere would give it a significant speed. So then adding elements. So here I started off with an empty hash and just added elements to it. Added 10, added 100, added 1,000. So this is kind of like creation, but doing it one by one by one, pushing them to the end of the hash. Here, again, hash ordered pretty handily outperforms most of the modules. TIE index does pretty well along the way. It's pretty close in terms of its numbers. So this is 368,000. This is 300,000. TIE xhash down to 263,000. So again, 30–40% speed difference, adding elements to an empty hash. Array as hash isn't doing so bad with a small size, but then falls off the bottom again as it gets to a larger size. So then we come to deleting, and I put the star on the deleting because this isn't purely deleting. This is creating an array and then deleting 10% of the elements back out of it. So things that performed well in creation do better here as well. So TIE index, which does very, very well at creation, and has a linked list, which makes deletions pretty quick, pretty handily outperforms everybody across the top for deleting things away. So if you need to create things and then delete them back out, TIE index is your module. But not if you need to actually access them. Hash ordered does pretty well. It's actually not too bad. Hash ordered, which is the one I wrote, does pretty well at small sizes and then falls off the cliff as we get up to 1,000 elements because it's having to do a linear search on the array to find the key to splice it out. Array as hash does OK up here, dies down here. So this is the sort of this mix of creation efficiency and deletion efficiency, and really needs to, following that suggestion, I need to find a way to split it out so we can see it a little more clearly, because I think it would be very interesting to see the algorithm differences across them. I think the linked list versions will do well here. So a TIE linked list hash, or LL hash, is kind of bringing up the rear at small sizes, but by the time you get up to a large hash with a lot of elements, it actually does really well. This is the linked list hash is the hash reference where every value is a reference to the data structure with the value and the next and previous keys. So all it has to do to delete out of that is just rearrange those keys. It doesn't have to splice anything out. Yeah.
So with a hash with 1,000 elements, that's saying it's 200. It could delete 269 a second. That's it.
It can create a hash of 1,000 elements and then delete 100 of them.
Oh, okay.
289 times a second.
Oh, 10% of.
Yeah, so it has to create the whole thing and then it has to delete the better. So it's just a lot of it's spinning on memory allocation.
So that whole process can run that many times a second?
Yes.
Okay, it's not like keys per second.
No, this is I can create the whole thing. I can create 1,000 elements. I can delete 100 elements, and I can repeat those two steps that many times a second. Sorry, Eric, and then Jordan.
Is linked list so low in 10.100 because it's struggling on inserting at first?
Probably.
Deleting is like fast.
Probably. I suspect if we could break it out, that the linked list hash, like TIE index, they'd float to the top because they should be very efficient at deletion. Unfortunately, they're not very efficient at a lot of other stuff all the time. So then sorry, Jordan.
Deletion of random 10%?
It is a random 10%. It's a pre-selected random 10%. So I pick 10% of the keys randomly, and then those get deleted. And they always get deleted in the same order on every run. So the hash has the same order for every run, and the deletion happens at the same order for every run. Any other questions about this? This is one of the weirder ones. All right. So then the next test was outputting the hash as a list. So this is, now that you've created it, and that happened independently, give me back key value pairs, which is sort of useful if you're having to serialize or you're having to send it over a network or if you print it out. So how fast is it at just turning this ordered hash back into a list of key value pairs? This was, I didn't show the code here, but it was actually one of the harder ones to write because some of the classes give you a very nice API for that. It's kind of like, give it to me as a list. Here you go. Other ones you're having to essentially do a map and iterate over the keys and construct that whole thing. And so some of the differences you'll see here are a function of how easy or hard they make it. Some of it's the underlying and without actually looking at the code, it's hard to draw perfect conclusions, but it's still sort of indicative. So array as hash, straight out across the top. Because if you have this internal array reference of data, your key value pairs, and you want that as a list, you dereference it and you hand it back. Very, very fast. And so if you remember, the array as hash is also very, very fast to create if you give it an array reference and you don't have it do a copy. So if you need to create an ordered hash that's very big and then pull that right back out, array as hash is very, very fast. But remember, array as hash was the one that was all the way at the bottom for all the fetches and all the sets. So if you just have data that needs to come in ordered and go back out ordered, this is actually going to be pretty good. If you have to manipulate it in the middle, you're going to have problems. Hash ordered, again, stays pretty good along number 2 all the way across. And that's actually kind of, I was interested because that, again, you have to sort of internally take your array of ordered keys and essentially run a map process to reconstruct the list from the array, from the hash, and pass it back. So it actually is doing a fair amount of work. But apparently everything else is doing even worse. I do actually want to sort of use this slide to highlight something. Yeah, Paul.
I'm just wondering, does maybe AH do want array and doesn't actually return any elements in list context if it's void context, and that's why it's so fast?
I don't know, and it's possible that I was smart enough to anticipate that and made sure that it was actually, it wasn't in void context. But I'm not sure. Maybe. We can, afterwards, I can pull up the code and check it. I want to use this slide to talk about something I mentioned early on, or referred to, was just the cost of tie. So if you think about Xhash, you can have Xhash as a tied hash, or you can have it as an object. And I believe that this TieX00, the object version, was actually one where you have to sort of take the keys and do a map and return a list. Tie Xhash using TH is the tied hash method. This is taking your tied hash, putting an ampersand, or, and basically just taking that tied hash and just reading it out in list context. So taking this hash and just reading that hash in list context is 40% slower than using the object-oriented method and iterating over. There is so much overhead every time Perl has to go and look up to see if something's tied, and then dispatch off to the methods, and then return all the data in the right way. The tie kills you every single time. And so if we go back, you'll see the same sort of split. Wherever there's an Xhash 00 and an Xhash TH, TH is always below. Every time you use a tied hash version compared to the object-oriented version of Xhash, you pay a huge penalty. So what were some of the conclusions that I took away from this? Hopefully you might take away from this. So first of all, tying sucks. Don't use ties if you can at all help it. If there's any way to accomplish what you want without using ties, don't use ties. Unless you don't care about speed. If you don't care about speed, then use ties. Have fun. For a one-liner, and you don't really care, it could be okay. The other thing was that module choice really, really mattered. Right? This is one particular task on CPAN, ordered hashes. I tested 7 CPAN modules out of the dozen or so that I found. And it was a 10 times difference in performance from the best to the worst on a number of these tasks. Sometimes it was only 5 times difference, but it was 10 times for some of these. So the choice of your module really matters. And I think that you really ought to look inside modules before you use them. When you're going to use something, actually open it up and see, like, well, how do they implement that? And does this implementation look sane and reasonable? Because if you see something like I did with Xhash, where I just said, well, why would they do that? Why would they keep the keys and the values in separate hashes, in separate arrays? Because that seems like it would be very hard to actually look anything up. And you sort of look at the methods and look at the amount of indirection and look at the amount of reference calls. You'll start to be able to see why maybe I should use this module versus this module. So it's not all just the shiny API on the outside. I think it's really important to sort of actually look at the code that's underlying it and get a sense for how is it going to perform. Unless you don't care about speed, in which case, of course, then, it doesn't really matter. And then the other thing I took away, to some extent, I freely admit to having a degree of confirmation bias here. Simplicity pays off. I'm a big believer in tiny. I'm a big believer in sort of a Unix-like philosophy for Perl, which is to take very, very small tools, which are well written and well composed, and putting them together in ways that do better things. And I find that small code bases have fewer bugs, they're easy to understand, and often cases they're faster. And that really was the case here. There's a lot less interaction, a lot less memory pressure. If you think about the TieLL hash, where it's allocating a hash ref every time you're storing the key, it's very, very expensive very, very quickly. And then having fewer ops per call really matters. Being able to do two dereferences instead of 6. matters. So I was actually thinking maybe I should do hash ordered XS and write an XS version of hash ordered. So instead of having to do all the iteration over stuff in Perl, do it all in C. So I could do all those dereferences outside the op tree, do the iteration over keys to produce the list outside the op tree, and make it real fast. So maybe by next year there'll be screamingly fast hash ordered. That was it. Any more questions? Yeah.
Did you consider balanced trees at all?
I did not, nor did I look at them. Part of the reason for that was because MongoDB already sort of supported tie-in hash. I sort of had a work reason for wanting to explore ways to sort of preserve a hash-like interface as much as possible, and I sort of just started to play around with it. I didn't actually look at trees to see if they would sort of make it better or faster, but I certainly welcome people to try and experiment. I worry a little bit about trees that you're going to run into the same problem that the double-linked lists have, which is you're going to be doing a lot of allocations and a lot of dereferences. And I think the power of hash ordered is that most of the time, if you're just trying to look up a value in a hash, you can get there in kind of like 1 or 2 dereferences, because you're just getting to the underlying hash. And the only time you need to know the order of the keys is if you're listing things out in order, or you're asking for the list of keys in order. So if you want to say, iterate over this list of keys in order, it's very easy to hand back the list of keys in order, because I've got that already. The only thing that takes a while to sort of assemble is if you want the key value pairs in order again, the way they were originally. That takes a little bit of work to assemble. But the rest of the time, those two kind of solve most of the use cases pretty well, except for deletion. What I didn't talk about here, but I talked about in the documentation, is that if you are, this hash ordered has like Xhash push, pop, shift, unshift, so you kind of put values on or off the front and back of that. Anytime you are taking stuff off, and I think that, so the feature is that if you push a value, push an element that's already on the hash, it'll pop it out of, it'll take it out of the middle of the hash, and it'll get added to the end. So if you push A5, A1 gets deleted out of the array, or A gets deleted out of the array, and then it gets stuck on the end of the array. So anytime you push or you unshift, if the value exists, you could actually incur the deletion cost as well. So there are some things that where the algorithm and the data structure will hurt, but I try to document that as clearly as possible. Yeah.
So when you're doing deletions or insertions,
yeah.
Well, insertions are easy. So you're inserting on the end. Deletions, you got to actually go in there, find it, and splice it.
Yeah, you got to search to the. I use listutil first, so at least that's an XS function to find the first instance. So search down there and splice it out. So it has to search. And then Perl has to do the
splice.
To rejigger all do the splice to sort of change the memory address. So that is overhead, but it's how many people delete from hashes a lot? No hands. So it happens, but
Search from a
so
when you delete from the hash,
yes.
you're looking at the key and you find the
Yeah.
in the hash, right?
I can
Or in the array.
go way back and find. Delete's expensive. So this is delete. And as Bulk said, there's probably some inefficient stuff that I'm doing around the edges. So, self and key shifted off of ampersand underscore, But it's, if it exists, if it doesn't exist, if it exists, I have to do something. If it doesn't exist, I just return undef. Here you go. So if it exists, then R is the sort of the reference to the array of keys in order. And then it says, find me the index. So go through this thing until the element equals the key. Walk through all that. Give me back the index. I wish. I think there's actually first. I think first listutil I think has first IDX in recent versions, but I didn't want to depend on it.
Isn't that in your first element? Which is your hash? The key lookup?
Well, the key is in the hash. I know that it's in the hash. The question is, I have to find where in the array is it so I can splice it out. So it finds the index of it in the array, and then it splices it out.
By looking it up in the hash.
No, because the hash has the data, not the index. So the hash is A1, B2, and it's not the index, it's the data. So it could be, A, dog, B, cat, C, elephant. And then there's just an array of data, and it has to like pull that element up. I'm pretty sure ListUtil has a function that would give me the index directly, but I think it's not in core back to 5.8, so I didn't. And then so once it pulls the element out of the array, then it's free to just delete out of the hash and hand back the value that delete gives. So is that straightforward? It's a little bit.
The splice is probably much more expensive than the linear lookup. Right?
Depends on how the linear lookup is implemented. Because the splice is just going to be Perl shifting a whole bunch of pointers around, which is not ridiculously expensive. It's all down at C.
I'm wondering, before I can shut it down, if you trade speed for space. And no, and that, well, that part, but in order to do that, if you've got one hash that's key value and an array of sorted keys, if you had another hash that was key index, there's the lookup.
Yeah.
But now it's maintaining that, so what's the speed and then the space?
Right, and so every time you store a value,
You store two.
You have to update that. And so that was sort of the thing that I looked at Xhash and said, well, you're storing, you have a hash of indexes, and then you have a data.
And that's what
value.
Xhash is
And I said,
doing, basically. Okay.
there's still a lot. There's a lot of extra sets, and I thought, I'm willing to have deletes be expensive because I think they're relatively rare in practice. And as the benchmarking showed, if you're deleting 10 elements out of a 10 LMA, 100 element array, not so bad. Yeah. Cool.
Instead of doing an exists, why not move the delete and just do the delete always? Even if the element doesn't exist. And then check for undef to avoid two deref chains. Not a hash lookup twice.
Yeah, that might be a way to do it. Pull this out value out first.
It's less clear, but it's a lot less ops.
Yeah, pull the value out first, and then if that value is, well, the thing is, the value could be the value could be undef. It could be a undef, and then I still need to delete a out. So I think I need an exist check. What I could do was pull off a reference to self data and not have to do that twice. And whether creating that scalar to avoid the dereference is faster or slower is, another sort of level of benchmarking. Any other questions? Yeah.
Yeah. Did you so do you do any overloading in the module?
The only overloading is on Boolean, so that if you use it in Boolean context, it will give you a value based on whether or not there are any keys. So like, the same way you can use a hash in Boolean context, you can say, well, if my hash ordered object, and that'll basically say, well, do I have any keys or not? And that's pretty quick because it's just checking the length of the keys already. But I avoided all other overloading. Other questions? All right. That's it. Thanks. Oh, yeah, Jordan.
You had mentioned at one point that one of the modules uses grep pattern to handle cases where the key is actually a reference.
Mm-hmm.
Wouldn't stringifying keys produce the same result with their value?
Not if stringification is overloaded. Yes, this was the problem with inside-out objects. If people remember inside-out objects, was that you were always having to take the ref adder of things to store to sort of index the data you were going. So I'm sort of half tempted maybe to make a version of array as hash that just does that sort of data structure of an array ref of key values and a hashed index, and see if without all the extra stuff that it does, how fast it actually would perform. But I think it would be at least comparable to Xhash, possibly better for some things, possibly worse for something. Because I think a lot of what hurts array as hash is just like Curtis wanted to put a lot of features in it that a lot of times maybe you don't need it. Any questions? All right. Thanks very much.
Thank you.